on the calendar as well. But if you'd like an email to let you know of these things, you can certainly check that out. By the way, my name is Dave Farina. I'm AELC Club President. Lane Davis, Vice President in the back. Tom Sprecher, Treasurer. So if anybody's interested in further information, just let one of us know. For our calendar for the month, we, as I said, are kind of winding down a little bit from our year. We've been very busy in past months. Over the summer months, we've had a number of events, including Star Watches, members only training sessions, and including some other things with Peckaway Valley does a Star Watch for kids with them. So we've been very active. Coming into the winter months, though, things start to slow down, and we do mostly the indoor lecture stuff. Coming up in terms of things you might want to check out, Leonid's meteor shower coming up later in the month, as well as a conjunction between the Moon and Venus. They're going to get very close in the sky. I'm sure Rob Webb, who you'll see in a bit, will probably talk about it in his Observing with Webb videos on YouTube. The Moon occults Venus. Moon is going to pass in front of Venus in the daytime. So that's something that you could check out as well. And Lane, do you know if that's something you're going to have a hard time seeing Venus, or you think because the moon's there you'll be able to focus on it?
Venus is brilliant. All you need is a pair of binoculars.
Binoculars. Okay. So 2 events coming up in December, and then have you got a chance to do 2016 yet? In terms of like this type of stuff?
What the schedule?
Yeah.
Yeah, that's all done and in there. Starts in March.
Oh, okay. No, I meant not in terms of Star Watches, but in terms of like astronomical things to look for.
I have some things in there,
Okay.
and I'll be adding more.
Okay, so Lane's the guy who puts that kind of stuff in, so if there's anything you have questions about with that.
And any of the events you can see up in the sky there, they're things you can see from Lancaster County, specifically.
Okay. So each month we have an Observing with Webb video. Rob Webb, he's not here tonight. He does these videos, and I wanted to, before I do the Observing with Webb tonight, I want to congratulate Rob Webb, because I was driving home on Monday evening, and while I was driving home, you have that on? Okay. While I was driving home, I heard over All Things Considered NPR, 89.5, that they were going to be talking about planetariums soon. And Rob and I both run planetariums, and I work in Manhattan Township School District. He works in Peckaway Valley School District. And I thought, wow, Rob would probably enjoy this, because I know we just talked recently about his planetarium. And so I called him. And I said, hey, there's going to be this planetarium thing on if you wanted to listen. He says, oh, that's interesting. He says, maybe I'll be on it. And I was like, okay, well, I know the Lancaster News just talked to me and him about a week before. I said, no, it's not the Lancaster News. It said it's NPR. It's about something national. He was like, no, they talked to me the other day. And I said, wait, what? And he's like, they called me. Maybe I'll be on. I said, okay, wow. Well, a few minutes later, and I actually put this right on the website here, so hopefully it doesn't bring anything. I haven't checked. This is my first test. And this website takes a little while. So I'm waiting, and about 10 minutes later, the piece started, and you can actually go to our website, go to the Observing with Webb tab, click on this link. It'll probably load forever like it's doing here. Hopefully come up soon. I want you to be able to hear it. It's a short clip. But anyhow, Rob's voice came over the radio for the National Public Radio. So someone local, Rob Webb, one of our members, was on NPR, which I thought was awesome. So looks like it's not going to cooperate with me, so I'm going to back up. should work, I don't know why. Okay, so this is Rob. I'll start by playing tonight the Observing with Web for November 2017. 2016. Wow. Why is it not working? I just had internet connection, and my entire discussion tonight will require internet connection, so give me just a moment here. See if I can't plug in directly. Wi-Fi is not working for me. Let's try that again.
See if you can do any of
All right, well, I'll just, what I'll do is I'll go to our website here. So we also have a YouTube page, so I'll just play it directly from YouTube. Excellent. Within YouTube, if you go to our playlists, you just type in Astronomy Enthusiasts of Lancaster County on YouTube, go to our playlists, and I was going to show you this anyway. I've actually made a little link here with only 3 videos in it for now, 2 of which I'm going to show you regarding tonight's topic. I also have an Observing with Web tab. We're also recording right now, and the AELC meetings from now on are hopefully all going to be videotaped. I've got 2 out of the 3 I've taped already up. So if you want to ever look back here, that's the whole idea.
Hi everybody, and welcome to Observing with Web for November 2015. November is not as interesting as October, but still some pretty cool stuff. We've got some close encounters, similar to October, but not as many, and not as tight. And the morning planets are going to start spreading out a little bit throughout the month, but we do get some more time to take a look because daylight savings time, however you say it, ends on November 2nd, and yeah, it's getting dark out. We've got longer periods of night anyway, so it's a good month to get out there. Plus you get some time off around Thanksgiving to go out and do that, assuming the skies are clear. So anyway, I'm going to talk about the planets that we can see, and then talk about the events, tracking the moon, and then go through the constellations real quick. So as far as planets that you can see, at least with your naked eye, typically we usually have 1 or 2 around sunset, but if you take a look up here, and I'm going with daylight savings time off, so on November 1st, 2nd, 3rd, you might be able to catch Saturn. You might. Now the thing is that Saturn's pretty low on the horizon. In fact, right around sunset, it looks like it's only about 10 degrees above the horizon. That's a fist width. Held at arm's length. So not very high, and the dusk is going to interfere a little bit. But it is there if you want to see it, at least until November 8th. After that, don't even try it. But that's going on over there in the west. And let's see, I don't see any other, oh wait, there's Neptune, but you need a telescope to see that. Oh, there's Uranus, but you need a telescope to see that, and I'm not going to cover that. So let's let the night move on. Oh, the Pleiades are rising, Taurus is rising, Orion is rising. Let's see, oh, really nothing. Oh, there's the moon on November 4th. Oh, here we go. Here's a cluster of planets. In fact, that's what I want to talk about right now. Venus, Mars, and Jupiter. In fact, let me go to November 1st. And if I zoom in, November 1st, here we go. If we zoom in on November 1st, you'll see Jupiter above Mars and Venus. Now, as we go through the month, you'll notice something. In fact, let me zoom out a little bit so we get the whole thing in. Let's say we go out at around 4 a.m., not daylight savings time, Eastern Standard Time. What you'll notice is Mars and Venus on the 2nd are very close to each other. It's only about a degree away, and Jupiter is up higher. And then as we go through the month, Venus, when you're on the moon, Venus gets lower and lower, and Jupiter gets higher and higher as the month goes by. And finally, by November 30th, you notice that Venus and Jupiter are on opposite sides of Mars and pretty far apart. I believe it's about 12 degrees between Venus and Mars, and about 20 degrees between Mars and Jupiter. So November is another good month for getting out there in the morning. Even as sunrise starts around 6 a.m., you can still see Jupiter, Mars, and Venus up there pretty bright in the morning sky. But anyway, that's what's really going on there. Mercury is another planet that you can see with your naked eye, but not this month. It's lost in the glare of the sun. So, all right, let me go back and go back in time to November 1st, and let's talk about the things that you can see or do the events. First of all, on the 2nd, daylight savings time ends at about 2 a.m. And also on the 2nd, like I just showed you, we have that conjunction of Venus and Mars. They are about a degree apart from each other. Okay. Venus is going to be pretty big, pretty darn bright. That's an easy one to find in the morning sky. You'll have to look after 3 a.m. in order to see those two. And yeah, not much really happens then until the 6th. Now this is nice because on the 6th, you get off in the east-southeast, you get Jupiter, the Moon, Mars, and Venus, all in the same area, okay? And what you'll see on the 6th, the Moon is going to be to the right of Jupiter, and by about, I think just 2 degrees, which is pretty cool. That's about pinky and your ring finger held at arm's length away. And then on the 7th, the next day, the Moon actually gets a little bit lower and close to Venus, and you actually get this nice conjunction, for lack of a better term, of the Moon, a nice thin Moon with Venus off to the left and Mars up and to the left as well. So that's pretty neat on the 6th and the 7th. You can see that conjunction of 4 celestial objects all together. And then you may have been noticing the Moon, day by day, is getting thinner and thinner and closer to the Sun, which is off in the east. And let's see, oh yeah, it's right there on the 9th, and then 10th and the 11th, that's when we have the new moon. Can't see it at all. The moon then, over the next couple of days, becomes a western object, where it's off in the west around sunrise. But that doesn't happen until, oh, did I miss it? Oh, I gotta put sunset in, that was my fault. Sunset, there we go. So sunset on November 12th, it's technically right next to 7, but you won't really be able to see it. 13th, 14th, and you notice the moon gets thicker and higher every day. And on the 17th to the 18th, we do have a meteor shower, but it's the Leonid meteor shower. You might only see a dozen or so under very clear skies, so it's not one you really want to travel for or make any crazy plans. But if you're out, go out and take a look at the sky, and you might just see a Leonid meteor. How do you know if it's a Leonid and not something else? Well, if you see it across the sky, just trace it back, and if that trace goes back to Leo the lion in the sky, well, you saw a Leonid. If not, then it's not a Leonid, it's whatever id of whatever constellation it went back to. So anyway, 17th and 18th, that's the peak of that meteor shower. And then on the 18th, 19th, you see we have a first quarter moon. The right half is lit up. You might see it when it's still daytime, but you can pretty much see that from sunset all the way into midnight, but that's when it sets, around midnight. Let's see, and then over the next couple of days, you have the first quarter moon gets thicker and thicker and thicker and thicker until November 25th, which is when we have the full moon, the whole thing is lit up, and you can see, you can see that for the entire night. Another cool thing is that if we go to, let's go to, let's see, the 25th, I believe, let's go to sunrise, but let's look at the west where the moon is. Let's go to the next day. Now, you might be able to see the moon occult or cover up Aldebaran. Now let me select the moon, let me center it on the moon. And so what you'll see is as time goes by, right about now, right as the moon is setting that morning on November 26th, you might be able to catch that star go right behind the full moon, which would be pretty neat to see. You probably want a telescope because it'll be nice and steady, but it's definitely worth looking at. And those are really the events for the month. So let me do a quick little tour. Let's go to November 15th. Now I'll do a quick little tour of the constellations. Now, the northern constellations are pretty easy because they just sort of go around and around. They're always up there. Ursa Major, or the Big Dipper. Let me go back to sunset. Let's go to let's go to 6. Big Dipper's going to be very, very low on the horizon. Draco's wrapping around the Ursa Minor and doing a U-turn to keep his eye on the Big Bear. Surrounds its little bear prey, keeps an eye on the Big Bear. Then you've got Cepheus up top and Cassiopeia pretty much up top. You can maybe catch some Milky Way going through Cassiopeia. But anyway, let's look toward the west. These are the constellations that are setting right about now, and you see the the summer constellations of Cygnus, Aquila, and Lyra, with the 3 brightest stars in the summer sky, which would be, wow, my brain just went dead. Vega, Altair, and Deneb. Wow. Those 3 bright stars make the asterism we know as the summer triangle. But they're going to set as the night goes by. And if you look to the left, or toward the east, you'll see the great big square of Pegasus, with the Andromeda curves coming right off of Pegasus. Okay. And if you look more toward the east, the winter constellations are starting to rise. So if you get up a little bit later, let's say midnight, they will be pretty high in the sky around midnight. Orion, the sideways bow tie in the sky, is up there, along with Gemini up and to its left. Orion is up here. Taurus is over here, that V constellation. And yeah, I'd say those are the ones you really want to look for. I'll talk more about the winter constellation in a future episode, but that's what's up in the sky for November of 2015, and I'd just like to wish you very clear, dark skies, and hopefully you get to see those morning planets.
We're going to next go to Lane. Lane has a picture he would like to share with us. He's going to display it from your computer.
No, I'm going to use the library computer. Sorry, just take a moment. I have a dedicated astronomy camera that can look really deep into the sky, and I love to explore it. I want to show you something that this is by no means my discovery. In other words, I found something unusual in the languages, and it took me a while to dig up the information off the web on exactly what it is, and I want to share it with you. But first, let me show you a few things. In this, the image I'm going to show you in a few minutes, not the first image, there's an open cluster of stars, which is just like, they're typically a roundish shape of lots of stars concentrated in a single area of the sky. And another item that's in there is what's called a reflection nebula. And another object that's in there is, well, I'll tell you about it in a minute. First of all, let's start with the reflection nebula. This is the Pleiades star cluster, and this is a typical reflection nebula. What's happening is these brilliant stars are moving through a gas cloud and gas and dust, and you're seeing the light from these stars illuminate that gas and dust, and it's always blue because these stars shine mostly in ultraviolet light, and blue light. Now, the other thing is, what you see a lot of up in the sky is an emission nebula, which looks something like this. This is a typical one. It's red. All right? It's red because this is ionized hydrogen, and the light out of ionized hydrogen is red. It's this color. What's ionizing it is a collection of brand new stars in here. Once again, lots of ultraviolet light, enough energy there to ionize the hydrogen gas cloud there. So you notice this one is red, the other one, a reflection nebula, was blue. This is called an emission nebula because the gas itself is actually emitting light. It's not reflecting. Now, on to, this was the image I took. And I knew this was here. That's the open cluster. You can make it out. Now, all these stars, of course, are in the Milky Way, our galaxy. So they're relatively nearby. And you can, this field right here is kind of in the middle of the Milky Way. So that's why there's lots and lots of stars here. But you can make out that concentration of stars right here, which is the open cluster I was trying to image. And I was also, at the same time, trying to image this reflection nebula right there. Okay, so I was looking for a star cluster. That's what a star cluster looks like. And I was looking for a reflection nebula, which is, this looks like a reflection nebula. But let's see, let's zoom in on this. And if I can figure out how to get here. And I'm going to show you something. Okay, there's the reflection nebula, but does everybody see like that little piece of red light, that gas right there? There's a little bit here, a little bit there, quite a piece here and here, but they didn't look like a nebula. You saw what the emission nebula looked like. It was big and it had a lot of light in it. These are just tiny little things. And so I wanted to find out what they were. And so I went out on the web and looked up any information on this object that I could find. And after a while, I managed to dig up a rather obscure article at the University of Kansas. Some astronomers there had been studying this particular nebula. And it was only then that I found out what these red things are. Now, back to that emission nebula, the big red one. All that light is being emitted at a very specific wavelength. And what I wasn't sure of is, although this red looks an awful lot like that other red, I wasn't sure it was exactly the same. So I had first shot this out of my backyard in the north end of Lancaster County, and I waited until the next time I was up at Cherry Springs State Park in Potter County, which is a really, really dark place. And there I was able to get a better picture because there's not as much light pollution in the background that we get out of all the city lights and suburban lights. And, but at the same time, I happen to have a filter for that camera that will record just hydrogen alpha light. And I'm not going to show you that image because it's really, really dim, but I shot it, and sure enough, the only thing that shows up is these little red things. In other words, the filter blocks everything else, including the stars. You can't see them. So that proved to me that's hydrogen alpha light there. And you normally associate that with stars, like I said, being developing. So, here was what I left, what I found out on the web was those little streaks of red are actually emitted by a brand new star, protostar it's called. This is the gas of the disk of dust and gas that normally envelops a star like that, so that you can't see the star itself. But these jets come out the north and south pole of the star. And this is an artist's rendition, but let's look at a real one. And that real one is from Hubble. Okay, that's the disk of dust and gas around a star. And here's one of the jets coming out. It's red. Another protostar, a jet. This is a much closer image. It shows you all the knots of turbulence in that jet coming out, but it's still very similar to that. So what's happening? And I never knew this. What's happening is those little things up there are those red spots are the location of where a star is formed. So I learned something out of this. Pretty interesting. By the way, this nebula is about 3,000 light years away, and the star cluster is about 6,000 light years away. So even though they're pretty close to each other, about a half a degree apart, they're still just line of sight. In other words, in distance, they're very far apart. Any questions about that?
Is that like a brown dwarf star?
No.
Like the red?
No, that's a real star. That's just first starting up. Okay, in other words, it'll turn into a real star like the sun. So it's not a brown dot. Brown dwarf is a failed star. It never really shines. It never generates its own energy. Yes?
You use hydrogen alpha to look at our sun, right?
Yeah?
Yeah. So, but our sun is not a new star, but
Right.
so.
In other words, our sun may have produced these jets of gas, the red jets of gas,
when it
but
was
not now, when it was young.
when it was young. So later, the sun or a star produces much more. Is that right?
Much more, no, it produces the most energy when it's first starting up altogether, and that's because it's producing energy over a huge spectrum of light, anywhere from infrared up through ultraviolet and sometimes more. When a star settles down, most of its energy output is producing more energy, but in a narrower range of the spectrum, if that answers your question.
Well, I wasn't sure what my question was even myself.
Now, would they have been developing maybe like 1 million years ago? Is it about,
No, this is
or is that going to be curved?
we're looking at it like it was 3,000 years ago. These stars, according to the article on the website at University of Kansas, the stars are less than 1 million years old, which this is only 3,000 light years away. So we're seeing them as they were 3,000 years ago
1,000 years before Christ.
versus a million years of age.
So
So
we're back in time.
I'm done.
All right, thank you, Lee.
Yeah.
Interesting. And to answer, kind of follow up on your question about what, our sun, we look at in the hydrogen alpha protostars, before even they start producing the jets that Lane showed you, you can start detecting them by looking for infrared. They cause it heating up of that surrounding gas bubble that's around them, and heat is infrared energy. So that would be the type of light, if that helps to answer what you were thinking.
It was like our son is making it now, so that's why we can see it now through a hydrogen alpha filter. So I was just
Yeah.
trying to figure that out.
All right, so let's get started with our discussion for the evening. Before we do, I just want to kind of show you, this is kind of what I've been doing for quite a while. This is my high school webpage that I use with my students. I'm actually in the process of moving it over to a new program. But anyhow, the project that I'm basically going to share with you tonight is one that I started 2 years ago with a NASA astronaut. And the NASA astronaut that I talked to is a guy right here named Charles Camarada. Dr. Charles Camarada is an astronaut. He was up on, I forget which STS mission, space shuttle mission, and he now works in Washington as in headquarters for NASA. He's an engineer by trade. He was involved in the fact-finding when the Columbia broke up in the atmosphere, and he moved to headquarters shortly after that. He was one of the people who determined that Columbia broke up in the atmosphere due to the impact of a piece of foam from the launch itself, and helped to come up with some of the procedures after Columbia, before the space shuttle was, the program was shut down, to try to make sure that it was safer. For instance, looking at the bottom of the spacecraft with a robot arm and trying to get a visual understanding of if there was any damage during launch. So this is the guy who basically helped me to find out about the Asteroids mining project, which I'm going to be speaking with you about tonight. As I said, there's a number of things that I have up here on the YouTube page, and I'm going to be referring back to them periodically throughout. So if you wanted to,
Hi, everybody.
if you wanted to go back to our webpage at any time to view these, I would definitely check that out under the playlists. So asteroids is something that we've been monitoring. Why would you want to monitor asteroids, other than just the fact that they're up there?
See if I can hit us.
Okay. One of the common things that many people think of whenever you say the word asteroid is an asteroid impact. We know they happen. It has happened in the past. We have strong evidence that these asteroids have done some major destruction in the past. For instance, the mass extinction of what we call dinosaurs was due, at least in part, by an asteroid impact. And so we've got a list of all sorts of asteroids, and we've been, over the years, collecting information about asteroids. And so we've got all sorts of websites here that I'm going to try to link in for you, just show you some basic information on them, because we know quite a bit. So the first thing I'm going to show you tonight is the asteroid discovery from 1980, which is not that long ago, up until 2011. So that's the best data I could find at this point. So they're going to start off.
There's no need to be afraid.
So you're going to start to see surveys. They're taking surveys of the sky, and you're going to see wings lighting up. When they light up, that's the discovery. You can see the orbit of the planets and the basic location of where these are found. And you'll notice we're getting in more and more slowly. Keep an eye on the numbers down bottom here. 11,800. Constant monitoring now. Very little downtime, almost always finding them. New survey came online. More information, a lot faster. Constantly finding vast amounts of them. The numbers getting extremely high. Thankfully. Hit 50,000 just now.
So the blue
New survey's definitely on again.
Does the blue circles represent the planet?
Some of them do, yes.
Some of them.
They were always there, we're just discovering them year by year.
Correct. So we're at over 200,000 now by 2003. And you can kind of really make out now the asteroid belt.
The large blue one at the end,
That would be Jupiter, I would believe, there. This.
yeah.
The discoveries are following Earth, of course.
Nighttime side of Earth, and directly away from the sun at all times. Yes. So you're trying not, you're seeing the reflection of the sun off of them. That's why, if you notice, it's always away from the sun. They're never looking over here. Now you get some of that bidirectional discoveries. So more than one survey going on at once.
What do the colors indicate?
The green.
I'd have to do a little refresher on that. I think that it has to do with the classification of the different types of asteroid.
It doesn't have to do with what's actually out there. It's just.
So basically, like was said earlier, these have always been out there.
Right.
We're just discovering them, and so logically it makes sense. You find the biggest ones first, and then as time moves forward, we're finding smaller and smaller and smaller objects. Some of them with visual observations, some of them with infrared observations, some of them with radio observations, different types of telescopes, and we just keep gaining them over time. And I don't know what the last number that was there. Can we see that towards the end? How many were there? See if we can see the very end here. The number went away.
Maybe it needs to be a full screen.
Yeah, I think so. Yeah, I just wanted to get an idea here of how many it ended with. About over 500,000. So, by 2011, over 500,000, and we continue to discover them at that rate or higher. It's very likely that there are millions of these objects, and this was just showing you the inner solar system. There's quite a bit more out in the Kuiper Belt, beyond Pluto, around where Pluto's at. So that's definitely not included here.
And are there larger numbers further out?
Yes.
How do they know you're very unique? Are they tracking each one then?
Yes.
Once they discover it?
Yes.
So they're tracking 500,000 known asteroids.
Yes. That will become eventually very important to know where they are, because if you were hit by one of them, that could be a problem. So we, in fact, even in low Earth orbit, we're keeping track of debris, both man-made and naturally occurring. For instance, back during the space shuttle era, when they were doing some of the building of the ISS still, the International Space Station, one of the astronauts she dropped her wrench and tool bag. We now have to track that. And it's trackable. We can actually see her tool bag flying through low Earth orbit. I don't know if it's fallen into Earth orbit at this point and crashing the atmosphere and burn up, but for at least a little while we were tracking it, because if that were to hit a spacecraft, that's done. You're toast.
The numbers are not increasing, it's just that we're able to see more of them as time goes by.
Correct. Yes.
Thank you.
Yes. There are likely millions and millions of these objects out there. It's just a matter of finding them. Correct.
Now, is that observation or that image done with a Hubble telescope? Or?
No, these are ground-based observing for the most part. Hubble is not used in a survey manner. Hubble is used in a way that once we've discovered something, we train Hubble's eye on it. Hubble has way too much to look at, and it's way too good of a telescope to spend our time on things looking for them.
Batteries though.
Okay, thank you for that. I don't know how. Ah, here it is. Okay. Good. So, this is, like I had shown you there, just a NASA webpage. I thought it was NASA. There are many different groups of asteroids, so we can look at like the inner solar system, top view, looking down, and just get an idea. And once again, there are different classes, and they tend to fall into these patterns that that's kind of the classification scheme appears to be. So the color coding, yes, it appears to be different things. And we've got the bulk of them found within the asteroid belt for the inner solar system. One common misconception with this, and it's almost every Hollywood movie you'll ever see, and I don't think it's going to go away, is that when you're flying through an asteroid field, that somehow, and in every way you look, that you're going to have an asteroid in your way. And you got to navigate around them. That's not true. An asteroid field, although there's many objects here, space is really, really big. And these things are tiny. Even if they're the size of this room, that's considered tiny. Okay? So try to get yourself out of the mode of thinking about flying through an asteroid field and having to dodge things. It's likely you wouldn't even see where they were if you were still right within it, because it's that dispersed. Even with millions and millions of objects there, it's still that dispersed. Sorry, I'm going to be clicking around all night, it looks like, because I have it set up so I can...
A few years ago,
Show you
Jupiter was hit by some massive asteroids. And they saw,
Shoemaker Levy 9,
yeah,
back in like the early 90s.
no,
97.
this is like 2000, like about 2000 something, like 2 years ago, was a Jupiter hit with these big asteroids, and we saw, and it was an amateur astronomer that took pictures of these big gaping holes.
Yeah, I think that was in the 90s.
No, it was only like 2 years ago. Wasn't it 2 years ago?
If you're looking, talking about the Shoemaker Levy 9 was when it hit by multiple things and the big holes were there.
Yeah,
That was like 97. I'm not sure, unless there was something new that I did not hear of.
it was just a few years ago.
So one of the things I'm going to try to make accessible to you is this database, which is a way that we can use some of these criteria that we were talking about, these orbit classes, the different colors, to search for asteroids. And you can search by many different ways, different parameters. I'll be clear, I don't know what all these parameters mean, but you know, certain things like diameter, I think just makes sense. So let's say you wanted to find anything that was greater than or less than 1. Okay, and then you can add that here and then go down through here and generate a table. Now, I will tell you this thing is a NASA webpage, it's government funded, and it works about this well. But the reason you need to do, what you need to do is you really need to refine the data. Unlike Google searches that can give you millions and millions of things, this will give you an error if you don't hone in on something. So you have to kind of add a few more things in there. So for instance, someone said earlier that if it hits us, one of the main things that we need to consider, and this is a reality, is that near-Earth asteroids do in fact exist. It's not just some worry that we have that's not founded within reality. There is a real chance that at some point an asteroid will become dangerous for us, and we're trying to make sure that we are aware of that prior to it hitting us. So NASA and the US and world governments are all very interested in keeping an eye on these NEOs, near-Earth asteroid, or near-Earth objects. They can be asteroids, they can be comets, they can be a shoe flying through space. They want to know what they are, and they keep track of them. So by adding a bunch of parameters here, let's see if I can make it work now. Probably not. Yeah, 42 matching objects, but nothing matching my description perfectly. So, you know, just play around with this and get this up on our website at some point and make, you know, try to find these objects. Now, within all of this, NASA is currently in a transition period. We're done with the space shuttle. Everybody thinks we gave up. And we somehow, now we're paying Russian spacecraft to go up and private industry. That's true. We are in a transitional period though. And that transitional period is pivoting to something new. That something new is deep space. NASA wants to give away the low Earth orbit to industry. They want commercial space flight. They don't want to have anything to do with it anymore. They want to go to Mars. They want to go back to the moon. And they want to go to asteroids. Three-pronged approach. The moon is third. Mars is probably going to be the long game. And in the short term, we're going to probably be visiting asteroids. They're easy. They don't have a lot of gravity. You can go up to one. You can sample it. And we also want to redirect one. We want to capture it. Maybe about no more than 10 meters across. A little more than 30 feet. We want to grab onto the thing. Bring it back. We want to put it into the moon's orbit. And then it's close by, we can study it. So NASA has a plan.
Sorry, you mean the same orbit as the moon?
It's going to orbit around the moon.
Around the moon, right.
Around the moon. And NASA has a plan that they're working on. It's called the Asteroid Grand Challenge. And this is kind of what I did my project with my students on. So the question is, how do we get an asteroid from the asteroid belt back to the moon? Part of that is, first off, how do we detect them? not trying to do that. First off is how to detect them. And, you know, we're looking, like I said, for something smaller than 30 meters. Anything too big, and it's just not going to be possible. We would need way too much energy to bring that thing back home. Too much rocket fuel. So one of the things, trying to find this. So one of the things that they're doing, I think maybe it's the gallery, is they're thinking of a big trash bag. Okay? They're going to go up to the asteroid. They're going to take this big trash bag thing, put it around it, and then they're going to cinch up the trash bag, like you close the trash bag with those, you know, things up top. And they're going to close it up, and then they're going to pull it as close as they can to the spacecraft, and then they're going to slowly move away and pull it with us.
How do they break it out of its own orbit?
It really is not in any really strong gravitational area like a planet or a moon. It's there, it's kind of got its own orbit, but that orbit is simply like an area where, so it's beyond Mars, right? And between Mars and Jupiter. There's not a whole lot there. So when we're pulling it away from its gravity of other asteroids, it's really not going to be a whole lot of a problem for us. What will be the problem is kind of making sure that the actual process of kind of wrapping this thing up for moving it goes without a hitch, because there's not going to be an astronaut there. This is going to be a process that's done fully by robots. And we've never done this before. We don't really know what they're made of until we can study them. So we need to find one. We need to find one that we have properties that we want. Now, what kind of asteroids are there? Does anyone have any background with knowledge about asteroids, meteorites?
Some are made maybe with iron.
Okay, so we got some that are made of iron. What else could be in? Ice.
Rock.
Rock. Okay, and every combination in between. Think failed planet, or planet that never became. You've got all the stuff that makes up a planet, but if you've got one that was more iron, that could be good for bringing back, we wanted to learn about the inner workings of the inside of what a planet would be made of. Back in the early times of the universe. So in terms of why do we care? Why do we want to capture an asteroid? Well, we want to know what the original universe, the original solar system was made of. Yes?
If you were pulling the asteroid, if you got into another planet's gravitational pull, what would happen then?
You would have to make sure that you were going fast enough. As long as you're going fast enough, you won't get pulled in. So you got to be. It's all about speed. As long as you're going fast, you don't fall into that planet's gravity. If you're going too slow, you fall in. Yeah, good question. So
Wrap it up very quickly. You can't just hang out there and wrap it up.
oh no, when you're out there, you can take a good old time. But when you say when you're coming closer to a planet, then you need to be going fast enough for you to be in orbit, to be able to enter an orbit. All an orbit is that you're moving fast enough. So for instance, the satellite's flying over the Earth. Here's the Earth, okay? Satellite flying over the Earth. If it were not for how fast it were moving, it would crash. It would fall down. All a satellite's doing to stay in orbit is going fast enough so that when it falls, the Earth is curving beneath it. And as it starts to fall, it is in fact in free fall. It falls, but there's no Earth below to hit. It's curving and going around at the same rate. So, with these asteroids, we're going to pull them into near Earth orbit in around our moon, that gets some people a little bit worried. The secondary reason why we're not pulling in something bigger than 30 meters is because that'll burn up in the atmosphere. Anything bigger, and you gotta start concerning ourselves. So this will burn up in the atmosphere, hopefully. Plus they can time it so that if it were to somehow get pulled in, which the moon is pretty far away, be clear about that. We're not gonna have to worry too much. The moon will get hit before we would. That we can control these things for the most part. We can know where a spacecraft's going to enter, and we can time it that it would only come in when it was over an ocean, if that were the case.
Now, if it's gonna orbit the moon,
Yes.
isn't there a possibility it could get out of the Earth, the moon's orbit, and head for Earth?
Highly unlikely. Highly unlikely.
But you said it would burn up in our atmosphere.
The majority of it would likely, that's one of the reasons why we're limiting the size of it, yes.
Smart people working
How
on
big was
it.
the asteroid that landed in
Yeah,
the ocean?
I wonder if there's.
Lane, do you remember how big the Russian asteroid was?
Is it
Meter?
a whole lot of cockroaches?
Yeah.
How big across that would be?
I think it was only about
Space bag.
10 feet in diameter.
10 feet in diameter. So that it definitely would not be a good thing, but we're keeping it far away. So there's that like trash bag idea.
Exactly.
So we come in, here's the asteroid coming in, and once we get around it, it closes up. And this is actually an article. It's a feasibility study by a third party. So they're saying, the Keck Institute says, NASA, let's see if they are doing something that is actually possible. Is this really feasible? So there's third parties out there doing their own research. And let's see if there's any other cool pictures here. So there's ideas about how you would go about doing this, how you would bring a spacecraft out. First you'd launch, then you'd go out, separation and deployment of the actual spacecraft. Come around here, you get a lunar gravity assist. Okay, gravity assist just makes your spacecraft go faster. You're basically allowing it to fall a little bit into the moon's gravity, and then whip around and do another burn on your engines to get out. And when you get out, you're going to go faster than you ever could achieve without using that gravitational assist. And you cruise to the asteroid for about 1.7 years. Okay, then we're doing our capture, and then return 2 to 6 years to get back to the moon. Once at the moon, once there, we can do many things, as we said. Some asteroids are rocky. Some of them are what's called a carbonaceous chondrite, which is basically, it has a lot of carbon in it. And these chondrites that have carbon are very dark, they're hard to detect, but if we can get a good one, they have organic material on them. When I say organic, I simply mean they are carbon-based molecules. A lot of people think organic and they think immediately life. That's not true on the chemical version of organic. But we are hoping that we see precursors to life. Long chains of carbons that could potentially form life and possibly look for life. A lot of times these chondrites also could include some water, which could also be important to us. So NASA has multiple different reasons for looking at this scientifically. So you've got your age-old question of what is this solar system, where did it come from, where did we come from, with the life aspect, and just how our planets formed.
Don't we have examples of these asteroids on the planet Earth?
But they've been tainted by being here. This is going to be, by many accounts, different in that, so here's just more ideas, more how it would be packaged and things like that. Probably too detailed. With those, they landed here and things can contaminate them. Even if we were able to return something, we would, from some of the other missions that are being discussed, where we're going to go out and snag up a little piece of asteroid and bring it back, That's a little piece of an asteroid. You got this much to work with. The difference here is you're going to have a whole asteroid. And you're going to put astronauts to that asteroid and work hands-on. They're literally have, open up this bag and see what's inside. Like Christmas for the astronauts, right? They get to open up their present. This huge asteroid they just brought back.
So their workshop would be orbiting the moon?
They
would
could
go
then,
up-
correct.
They would have to fly to the moon, and they'd have to be out in their spacesuits examining the,
That would be the first start, yes. Yes. Okay, now, to kind of transition here, I've been trying to kind of show you where we are, what NASA's doing. But that's not the discussion tonight. The discussion tonight has to do with mining asteroids and the space economy and the future. This is the beginning of something very, very interesting. There are currently two companies, at least that I'm aware of, that are talking about where they would like to see us in 100 years. And I've actually taken the NASA, Dr. Charles Camarada, his idea for what he originally planned for, which he was trying to help NASA get ideas from students. And I took that and I ran with it. And I told my students, I don't want to, let's look at that, but then let's take that to the next step. Where do you, especially for the kids in the room, where do you want to see us in 50 years, in 100 years? When you're midway through your job in 50 years, which probably will be mid-career, right? 50 plus years of working, I would imagine. Because people are going to live to be about 120, we estimate, based on genetic medicine. So I'm hoping to live to 100. I'd like to see this happen. And so one of these companies, and I'm going to take you to both of their websites to be fair, is called Planetary Resources. And they think that mining asteroids is going to be at least $1 trillion enterprise. They have already done quite a bit in terms of planning, and they're really, they're getting some backing here from pretty important things like the United States Congress thinks they're going to do a good job. We also have their competitor, who, by the way, I would imagine they're helping each other at this point. I mean, this is really early stages, DSI, Deep Space Industries. Both of these companies are backed by major tech companies, the Googles and the SpaceX's and the tech industry billionaires. They've got money, more money than they know what to do with it. And so what do? They go to space and they do these ideas that are going to be 100 years in the future, because, well, what else do you do with $100 billion or something like Bill Gates has, right? So they're trying to come up with these ideas, and I'm going to show you a video for both of them. Try to keep this fair and balanced, as I said. Because maybe at some point you're going to be asked to, go to space, and you have a choice of which one you go to. So we'll go first with Planetary Resources, because I think theirs just does a better job with the beginnings of this, and then we'll go to Deep Space Industries, which I think is kind of seen even farther in the future. It's a different vision, different way of explaining things. Like, you turn the sound just a little bit again.
Imagine that you're on a road trip from Seattle to New York City. Now, what if there were no gas stations along the way, and you had to bring all the fuel that you'd ever need with you? You'd have no room left for anything. Well, in outer space, the problem is even worse than this. After all, judging by the space race of the 60s and 70s, you might have thought we'd have colonized Mars by now. But we haven't. We're trapped at the bottom of Earth's gravity well, which is so deep that escaping the first 300 kilometers takes more energy than the next
Low Earth
300
orbit.
million. It takes 50
And this is
kilos of
higher
propellant
Earth
to
orbit,
deliver just
geosynchronous
1
orbit.
kilo to Leo. But 4 more would get
Oh,
you
they
the
just
next
did.
35,000 kilometers. And 2 more, the last 300 million to Mars, to the asteroids, to anywhere in the inner solar system. But those 4 kilos to Geo each need 50 kilos to get into Leo first. And those 2 to everywhere else each need 4, which each need 50. This exponential nature of the rocket equation has us stuck hugging our planet. Planetary resources has had a Copernican shift in thinking. Travel beyond Earth's gravity well is nearly effortless. So, if fuel is sourced from space for space, we can avoid this exponential problem altogether. Fortunately, rockets run most efficiently on hydrogen and oxygen, which is just electrolyzed water and exists in near infinite quantities on asteroids. These future oil fields of space are also ultra-high-grade precious metal mines that lie unperturbed as the low-hanging fruit of our solar system, energetically closer than the moon, just waiting to be harvested. Mining asteroids could provide a fuel source 1,000 times more efficient than the brute force, bring everything with you approach used by the Apollo moon program. So how big is the space market when economics improved by 1,000 times? No one knows for sure. But neither did the Wright brothers at Kitty Hawk, nor IBM or Bill Gates at the dawn of their new markets.
Thoughts?
So they know that these resources are there on the
Yes.
asteroid. And again, what they went by really fast. What are these compounds that they're rubbing their hands over?
Okay, so great question. What are these resources? Probably one of the most important resources is water, H2O. Now, what can you do with water? Drink it. What else?
You can make it into heavy water.
Okay, it takes some refining. Sure, you can do that.
Use it for cooling.
Cooling, good.
Make fuel,
How?
fuel cell.
So first we need to break the water apart, right? Before we start breaking water apart, what else is water used for? We'll come back to that.
Growing things.
Growing things, yeah, food, right? To grow food. Plants need water. So we've got water to drink ourselves, we've got water to cool things, we've got water to make heavier versions of water, which take refining, and a pretty large amount of water, and to grow food. All right, so breaking that water apart now, use a process called electrolysis. It's really easy. Take 2 electrodes, stick it in water, 1 positive, 1 negative on each side of the battery. Use aluminum. It bubbles. The bubbles coming from the one terminal are hydrogen. The bubbles coming from the other terminal are oxygen. Why? Because water is polar, right? So when you've got a polar molecule, the hydrogens are going to get pulled. They have a relatively positive charge, right? Because the electrons are going to be stripped of them by that bigger oxygen. They're going to be gravitating towards that negative terminal of the battery. And that positively charged, or that negatively charged oxygen, because it's going to steal those electrons from the hydrogen in water, is going to be attracted towards the positive terminal of the battery, because negative and positive attract. It literally rips the water apart.
It's that simple.
And it's that simple, exactly. And it's something you could do with solar panels. It's something you can do with any type of electricity. And it's something I do in my classroom already. Like, it's literally a 5-second demo. Hey, in a battery, and done.
How do you get the water out of the asteroid?
It's there in ice form. So you harvest the ice. A lot of, especially comets, of course, but even asteroids, a lot of them we think are water, ice, frozen in place. So take the water, take the ice, gather it up, and at the same time, maybe get some other materials, which we can talk about in a second, and do this electrolysis. Now you've got hydrogen plus oxygen makes rocket fuel. You've got Tom said, fuel cells. Now I can store hydrogen over here, oxygen over here, let them interact and make electricity coming back out of this. So it's a storage device. We use fuel cells in the International Space Station right now. Once again, I've got a fuel cell, like a little demo in my classroom. It's really simple.
There's a lot of energy to convert ice to water.
Yes, but how important is it when, like they were saying, how hard it is to get water to space? For every, I think it's 50 kilos of rocket fuel for every kilo of mass we bring up. So you want to bring 2.2 pounds of water or 1 kilo of water up, you're going to need 50 times that amount in rocket fuel to get it there. Their idea is, you need water to survive, and why don't we just get it while we're up here?
Well, the point is, where do they get the energy to convert the water, the ice to water?
You could get it from many ways. You could use solar power. You could also use a like a nuclear device. There are options.
It would be mostly solar.
Mostly solar, yeah. And consider, solar in space is a lot better than solar on the ground here. We've got an atmosphere above us. That atmosphere blocks out UV. Space-based solar is like 35% efficient. Whereas ground-based solar is like, what, 10 maybe? Because we can't use the energy from UV, which we can in space. And that is our higher energy photons. So, there are challenges, of course. I mean, it's not, otherwise we wouldn't do it, right? So we get water, we got hydrogen plus oxygen. We're making electricity, we're splitting it apart. We also have rocket fuel. But what about the hydrogen and oxygen? What else could we do with it? What else can we use oxygen for? Breathe. Yeah. So now we've got a way to make water, food, and air. That's good.
It doesn't
We make rocket fuel, we can get home.
doesn't seem very elegant to be looking for millions of asteroids, and then you've got this immense operation to do to create these various things, and then you've got to put them in special places, and it just seems, it's not an elegant, I don't think
The
it's a
point
very
is,
elegant idea.
you're here on Earth. Once you get out of, this is representing Earth's gravity well, right? So once you leave Earth's gravity well, the average gravity of space is very low beyond this point. It does not take much to make your way around. If we want to leave this planet and stay out there, we cannot keep coming back here. And in order to stay out there, we need to have frontier towns, frontier places to go. And that's what this is about. This is like they were saying, driving across the country with no gas stations on the way would be a problem. And we need to be able to stop along the way. And this is our way of stopping, so we can keep venturing farther and farther. I'm going to show you next the next company, which is Deep Space Industries. A different vision, but very much the same. And actually, I'll have to come back to that.
With available powerful
In just a
trailing
second.
mirrors with industry-first LED rear guidance lamps. What will tomorrow look like? Our world is at its limits, and yet we all want more. And why not? Why shouldn't the future be brighter than today? But where will it come from? Simple. Our tiny planet sits in a vast sea of resources,
They're making this
including
thing too.
billions of
Those
asteroids bathed in the sun's free energy 24 hours a day. The same rocks that could fall from our skies also contain everything we could ever need, both out there and down here. It's time someone seized the opportunity. Deep Space Industries. Deep space is a new kind of company with a new kind of plan. We don't build rockets, we don't do astronomy. We are explorers and harvesters, makers and suppliers. As they say, timing is everything. And for space, right now is that time. In fact, some of the planet's most successful people are placing their bets on this new frontier. Meanwhile, NASA and others are planning new missions to the Moon and Mars, and new space facilities in free space, joining the billions of dollars worth of communication satellites already in orbit. And as they reach beyond Earth orbit, deep space industries will be there with the fuel, air, and materials they need to succeed and grow. DSI has assembled an international team of well-known experts and young innovators who are building our space legacy and creating new technologies and approaches to open the frontier.
Notice all the
We will
solar.
develop and prove ourselves in 3 areas: exploring and prospecting for asteroids, harvesting and returning asteroid materials, processing those materials for use in space and on Earth. Our early systems will be small and largely off-the-shelf components re-engineered for deep space. We will hitch rides on much larger missions with multiple ways to get into space, where our job really begins. With mission costs so low, we will be able to attract commercial sponsors and build fleets of vehicles to assure our success. Early markets will be satellites in need of fuel, government outposts and commercial facilities, and missions between the Earth and the Moon. As we gain experience and develop our systems, we will grow them as the frontier grows, so that when the time comes, DSI will be ready. We will be the gas station, the oasis for air and water, and the building supply center for the frontier. This is a long game, perhaps the longest ever. While we'll earn our way, the long goal is to create a better future for all of us through space resources. When the first asteroid is mined, deep space will be there. When the first space power plants come online, deep space will be there. When the first space colonies are built, deep space will be there. We can have it all. We can have an amazing future. The resources of space will lead to a renaissance both in space and back here on our precious Mother Earth. We are deep space. The frontier is coming, and our time is now.
So you'll notice a somewhat different take on this, but a lot of the same ideas, a lot of the same technologies. I want to highlight one thing that both companies are looking at, but this one in particular has highlighted pretty nicely in their video. What do you think's going on here? Space colony, maybe, yeah, some sort of spaceship or maybe some sort of deep space station. But what?
Manufacturing?
Yeah, exactly. They are literally 3D printing this ring, and this one is almost complete. So what they would do is they would have, because you're in this microgravity environment, there's not much to really have to hold this in place. And so we rotate the thing we're 3D printing out of the 3D printer, and we make it in this shape, circular shape, and it can just be printed off in microgravity and make the ring. Where are we getting this material from? From the asteroid itself. You wouldn't want, we were talking about launching water into space being hard to do. Imagine trying to launch iron. That'd be horrible. Iron's really hard to deal with because it's so heavy. So, it's really important. Remember, the number was 50 kilos for every 1 kilo of water. Also keep in mind, I think the number, if I remember correctly, is that also costs about $10,000 for every pound. So Why get this stuff from space? Because it's a pound of iron, or a pound of water, or a pound of you gain weight this holiday season as an astronaut means 10 more grand and more rocket fuel. So we've got to cut that out of the equation. We've got to get our resources from space if we want to leave this planet and go elsewhere. Bring it with us is not an option.
So I'm sorry, for detail, you mean $10,000 per pound or per kilo?
I believe it's per pound.
So
And I don't know the number.
2.2 that to
Yeah,
the kilo.
yeah, so it'd be $20,000 a kilo. Something like that is the last number I remember here.
But you've got to find the perfect asteroid to be doing all of these.
I think that they're aware of that.
Yes.
Who pays for these companies? Is it the?
They already have huge amounts of money from their tech industry that they already made their money on.
So it's not the US taxpayer that's funding?
No, these are private companies. These are private companies, and the reason, okay, the last part is why would you do this? Let me just kind of go back to this other thing. I'm going to go right to the end. Okay? The other part of this is, okay, so they've got money from this, and we got the ability to go out there. So they're estimating, $500 billion possibly, up to $500 billion in the fact that we can provide water for deep space. But why actually has to do with some of the other stuff. They showed this here. They were talking about precious metals. Inside these things, your electronics, are some of the most precious metals that we have, which is one of the reasons why they're so darn expensive. Computer chips are made out of silicon, right? If it weren't for the fact that it's too expensive, we would be making them out of germanium. Germanium's not as abundant as silicon. Silicon is glass. Basically, this entire planet's surface is made of silicon. So we can, and quartz is silicon dioxide, for instance. Sand at the beach, gather some sand at the beach, make a computer processor out of it. If we were to use germanium, we would have way faster computer chips. But we don't, at least for most applications, because it's too darn expensive. In these are not only just germanium and some other heavier metals, there's things like platinum in here. And the whole platinum group is extremely rare on Earth, but much more abundant in these asteroids. Much more highly concentrated, I should say. It's been discussed that an asteroid, just a few, maybe the size of a football field, would have more platinum than we've ever mined on the history of this planet.
How do they know that?
Based on the composition of asteroids and what we've done when we do find them. When they do land on this planet, we can study them. So the average composition of these particular types of asteroids, the iron-based ones, have huge amounts of platinum. Why? Because they were at one point the rocky core of some planetoid that never formed.
In this system, in our
Early in the solar
local
system. There's plenty of platinum in our Earth's core, down deep in the Earth. Good luck getting it.
Right.
So we go up to space, and here it is, parked in some asteroid orbit. So now we're looking at things that are worth something. Platinum, and the whole group of metals. And we could bring them back, or we could use them in space. And that's where they're looking at making those trillions of dollars, using those platinum group metals. So a few last comments, a few last things before we wrap things up. Let me just kind of click through here, see where we're at. Refresh this page, this looks like it crashed on me.
So DSI's been around for
A number of years, like just a handful of years. I think, like I said, 2013 I was trained in this, and they were already in existence then. And they're working slowly. Here we go. So these companies that are doing the space exploration are also starting to buy up 3D printer companies because they see the future of that technology, and they're going to need it once they're in space. Last thing I'll end with tonight is that, here's this guy, I just love this guy. Robonaut. Did you know we have a robot in the International Space Station that looks like this? Robonaut 2.
No.
It looks humanoid because we're trying to make it nice and, you know, something that people will be okay with. We even pad it so that if you touch it by accident when you're out, you know, in the space station, that it doesn't feel metallic and unliving. That it'll be nice and soft like a human. And it's currently doing a lot of things that maybe in the past we would have had people do. Like for instance, here I'll show you a quick little video. That's not a quick little video. Let me see if I can find something.
Together, we can build.
See if I can see him moving. So, you know, he's got the ability to move just like a human. He can move a wrench or screwdriver, and we have him doing these types of things already in the International Space Station. Of course, he's way stronger than a human, but it has detectors to know if I'm nearby that if Robonaut swings, he doesn't, you know, hurt Alex here. It has some fail-safes when it's around people, and the idea will be eventually that Robonaut gets him some legs. So at some point, we might be, I don't know, navigating around a planet, too risky for a human, but with Robonaut on the surface, you can act like a human, you can be hooked up and see through Robonaut's eyes. Being on the surface is not necessary. Robonaut's there, and he's stronger than you would be anyway, so maybe that's helpful. This is the kind of cool things that are already going to be possible within a number of years. They're on their way already. And the last thing I'll point out is that we are starting to see new types of propulsion. So the distances and the time periods that we were talking about with 2 to 6 years could be accelerated as these new technologies for propulsion make us go faster than in the past.
And I'm seeing a word, magnetoplasma.
Yes, this is the ion style drive, which I
It goes away with traditional combustion.
Correct.
Yeah.
You're literally throwing particles out the back of the spacecraft. They're ions. The ions are charged. Charged particles can be accelerated in a magnetic field. So you create a really strong magnetic field. You've got a fuel tank essentially of charged ions, and you throw them out one at a time over a really long duration. And that will provide you a slow propulsion speed up and acceleration over time rather than a single big push and then just drift. And the added benefit is that, you know, you get to use a lot smaller amount of fuel to go a lot faster. So, any questions about this upcoming industry? Who's buying stock? All right. I'm not one to use stock, but it sounds like a good idea.
Is it all of them, they have their own websites?
Oh yeah, they're established companies, and they're starting to do some stuff. One company's already showing you they're doing some of their own asteroid finding on their own, some of their own prospecting. And they're using like a Schmidt-Cassegrain, a little 8-inch telescope about this big, but it's space-based. So, you know, if any of you have a telescope, space-based telescope,
So it's a satellite.
they're trying to do some of their own prospecting, because then it's proprietary. They get to keep that information and not tell their competitors.
Oh, yeah.
Because right now, all that NASA has is open to the public. Anybody can have that information. So if they find it on their own, they get to keep that information. So let's say Planetary Resources finds a new asteroid, they're interested in it. They don't know about it, but maybe deep space industry won't. And that's kind of the branching out we go. The last bit of this is that the international world governments need to come together with some sort of an agreement, because we're not going to be the only ones up there. And at this point, we've said that no particular nation can claim a body like the moon, for instance. There's not a lot of clarity on companies. And companies own something, Are they allowed to just go out there? Do they have to pay some sort of international taxes on that? What does that look like? Or can they just go out and just take everything they want and not pay anybody anything? So that's, the governments of the world need to kind of come up with some sort of agreement here. And that's something I would expect to happen before most of this starts to take off. Because I don't know how else they can have public buy-in, literally the stocks and stuff. I don't know how they would ever get the funding they need to make this happen without people knowing it's going to happen, without government intervention. Yeah.
Have they found any, or do they think there is, any rare earth magnets on them?
I would imagine there's probably an abundance of all the elements in the periodic table. Whether there are ores, I don't know. I would expect that there would be.
Because if there are magnets, would be able to see which ones, because it'd be stuck together.
Anything else? Any other questions? All right, members, if you guys could stay for a little while, Lane needs to discuss nominations. We're coming up to the end of the year, and we're trying to determine officer positions and things like that. If you're not a member and you'd like to stay, that's fine, but we just have some housekeeping to do here at the end. Lane?